A photon has just arrived from the edge of time itself. This is the story of its homecoming, a journey from the fiery dawn of the universe directly to your world. You are about to witness the complete voyage of ancient light, from its first moments of freedom after the Big Bang to its final click in a modern detector. By the end, you will see the cosmos in a completely new way, understanding how a single particle of light can reveal the universe's deepest secrets. We will uncover how this primordial whisper holds the blueprint for everything, from the formation of galaxies to the ultimate fate of all existence. How does it feel to know you are connected to the very beginning of everything? The universe was not always a place of light and shadow. For nearly 400,000 years, it existed as a searing, impenetrable fog. Light was not yet a traveler but a prisoner, trapped in a relentless tug of war with a sea of charged particles. A photon born in this forge would be instantly snatched and scattered, unable to journey more than a minuscule distance before being absorbed again. This was the Cosmic Dark Age, a time when the entire cosmos was a single, glowing plasma, opaque and chaotic. Then, a profound transformation began. As the universe expanded, it cooled, and this cooling changed everything. Particles that had been racing freely began to slow, and electrons found their orbits around protons, forming the very first atoms of neutral hydrogen. This pivotal moment is known as recombination. It was the universe's great clearing. Suddenly, the paths that were once blocked were now open. The photons, once perpetually trapped, were finally set free. They decoupled from the matter that had held them and began streaming across the cosmos unimpeded for the very first time. This initial burst of freedom, this first scattering, created an echo that still fills every cubic centimeter of space today. We call it the cosmic microwave background. It is the oldest light we can see, a fossilized snapshot of the infant universe. But this snapshot is not a uniform glow. It holds faint, ghostly patterns, tiny variations in temperature. These minuscule ripples are the seeds of destiny. They are the gravitational blueprints for everything that would ever be. The slight over densities revealed in this light would, over billions of years, pull in more and more matter, eventually growing into the vast cosmic web of galaxies, stars, and planets. So how does this ancient echo help us understand our origins? By reading these subtle temperature fluctuations, we can reconstruct the universe's infant composition, its density, and even the nature of the fundamental forces that shaped it. This primordial light is our starting point, the moment our photon begins its epic voyage across an ever-expanding emptiness. This sudden clearing of the cosmic fog was the ultimate liberation. After nearly 400,000 years of relentless chaos, light could finally travel in a straight line. The instant an electron settled into orbit around a proton, creating the first stable hydrogen atom, the universe transformed from an opaque plasma into a transparent expanse. This pivotal event, known as photon decoupling, happened when the cosmos cooled to around 3000 Kelvin. Think of the decoupling surface not as a place, but as a moment in time, a single, shimmering shell from which the oldest photons we can possibly see began their endless journeys. As the renowned astrophysicist Alan Grant describes it, this surface acts like a photosphere for the entire universe, a final wall from which the first light escaped. That initial light was brilliant and energetic, glowing in the visible and ultraviolet spectrum. But the universe did not stand still. It has been stretching for billions of years since, and that expansion has performed a remarkable magic trick on the light itself. The very fabric of space has stretched, pulling each light wave along with it. redshifting that primordial glare into the faint, cold whisper of microwaves we detect today. This is why we now call it the cosmic microwave background. But these photons are not blank slates. They are cosmic messengers, each one imprinted with a unique story from its moment of birth. The direction from which a photon arrives, its subtle polarization, and its exact frequency are all a permanent record of its last scattering. They carry the faint gravitational signatures of the dark matter that was already weaving the cosmic web, and the echoes of the primordial sound waves that once rippled through the fiery plasma. The specific patterns we see in the polarization of this ancient light, for instance, tell a later chapter of the story, revealing when the first stars and galaxies reionized parts of the universe. The precise timing of this great emancipation itself is a crucial clue. Why did it happen exactly when it did? The answer is locked in the properties of the primordial plasma. The rate of the universe's early expansion and the specific density of particles, the ratio of protons to photons, all dictated that critical temperature threshold. It is a cosmic clock that tells us about the fundamental ingredients of the infant cosmos. With their freedom won, these ancient photons began their epic voyage across an expanding universe, a journey through a landscape that was itself growing and evolving in the dark. What did they encounter on their long road home? That first moment of freedom was just the beginning of a journey across an ever-stretching canvas of space. As our photon streamed outward, the very fabric through which it traveled was expanding, performing a slow, relentless magic on the light itself. The photon's wavelength began to stretch, much like a drawing on a rubber sheet that is slowly pulled apart, its lines elongating and reddening over billions of years. This is cosmological redshift, a direct and unavoidable consequence of the universe's expansion. The farther a photon travels, the more space stretches beneath its feet, and the more its light is shifted toward the red end of the spectrum. This relationship is so fundamental it is described by Hubble's law, which tells us that the recessional velocity of a galaxy increases with its distance from us. As physicist Elena Torres explains, redshift is the universe's way of telling us about its history of expansion. Each photon's frequency shift is a clock measuring cosmic time. We quantify this stretching with a simple number called the redshift parameter, denoted by the letter Z. This parameter relates the observed wavelength of light we measure today to the wavelength it had when it was first emitted. It provides a direct measure of how much the universe has expanded since that moment. For our photon from the cosmic microwave background, the redshift is staggering, with a value of about 1,100. This means its wavelength has been stretched by a factor of over 1,000 since it broke free during decoupling. This relentless stretching does more than just change the color of the light, it also dilutes its energy. The photon that began its journey as a brilliant flash of visible or ultraviolet light has been transformed into a faint whisper in the microwave part of the spectrum. This is precisely why we now detect the ancient afterglow as a cold microwave background rather than a blinding optical glare. So how does this remarkable effect allow us to map the cosmos? By carefully measuring the redshift of light from distant galaxies, astronomers can determine not just how fast an object is moving away from us, but also its distance and its place in the grand timeline of the universe. Redshift is the ultimate cosmic yardstick, allowing us to construct three-dimensional maps of the large-scale structure of everything that exists. This continuous stretching is a fundamental part of our photon's epic story, a quiet transformation that occurred across an almost unimaginable void. But its journey was not entirely through empty space. What happened when this ancient traveler encountered the growing cosmic structures taking shape in the darkness? As our photon journeys across the cosmos, its path is rarely a perfect straight line. It flies through a universe where space itself is curved by the presence of mass. When this ancient light passes near a massive galaxy cluster, its trajectory bends subtly, like a marble rolling near a deep depression on a stretched rubber sheet. This phenomenon is gravitational lensing, a dramatic confirmation of Einstein's theory of general relativity, which tells us that massive objects warp the very fabric of spacetime, causing even light to follow a curved path. Cosmologist Liam Chen describes this effect as a natural telescope, one that can magnify and distort the images of incredibly distant background sources. This cosmic lens does more than just bend light, it allows us to see the invisible. The way light bends reveals the presence and distribution of dark matter, the mysterious substance that makes up most of the universe's mass but emits no light of its own. There are different flavors of this cosmic deflection. Strong lensing creates spectacular multiple images of a single galaxy or brilliant Einstein rings, where a distant galaxy appears as a perfect circle of light around a closer one. Weak lensing imposes a far more subtle distortion, gently shearing the shapes of thousands of background galaxies in a way that maps the dark matter scaffolding between us and them. Then there is microlensing, a temporary brightening of a star caused when a compact object like a planet passes directly in front of it, focusing its light toward us. The Hubble Space Telescope has provided stunning examples, capturing galaxies stretched into long, luminous arcs and quasars mirrored into multiple points of light. These are not just beautiful images, they are crucial data. By analyzing these bent paths, astronomers can weigh the lensing galaxy clusters and create detailed maps of their dark matter halos. The precise amount of bending also provides an independent way to measure cosmic distances and refine key numbers like the Hubble constant, which describes the universe's expansion rate. How can we use these distorted images to test the very laws of gravity themselves? By observing how light behaves in these extreme gravitational fields, we can probe whether Einstein's theory holds perfectly or if subtle modifications are needed. This gentle curving of its path is another chapter written into our photon's long story, a permanent record of every massive structure it passed on its way to us. But our photon carries more than just a stretched wavelength and a bent path. It also holds a hidden vibration, a subtle orientation locked in from the very moment it broke free. This is its polarization, a directional quality that acts like a tiny compass needle pointing back to its origin. As it scattered off an electron for the final time, the photon acquired a specific vibrational direction, permanently imprinted by the local conditions of that hot, young universe. This polarization is not random. It encodes the detailed physics of the last scattering surface, creating distinct patterns across the sky that cosmologists can read like a cosmic fingerprint. These patterns split into two fundamental types, known as E modes and B modes. E mode polarization is generated by the density fluctuations in the primordial plasma, the same over densities that seeded galaxy clusters. We have mapped these patterns in exquisite detail, but the B modes are far more elusive. As expert Dr. Sofia Ramirez states, the B mode polarization is a holy grail in cosmology, as it could provide direct evidence for primordial gravitational waves from cosmic inflation. These are not light waves, but ripples in the very fabric of spacetime itself, theorized to have been generated during a period of hyper-fast expansion in the universe's first fraction of a second. Detecting this signal would be like hearing the echo of the Big Bang's birth cry. The quest to find it has driven ambitious experiments like the BICEP and Planck collaborations. They scan the skies from the pristine, dry air of the South Pole, searching for that faint, curling signature in the cosmic background. This search is incredibly difficult. The initial excitement from the BICEP 2 collaboration in 2014 was a powerful lesson. Their potential signal was later shown to be largely caused by polarized dust within our own Milky Way galaxy, a foreground contaminant that must be meticulously subtracted. This challenge underscores the painstaking precision required to isolate the universe's first whisper from the local noise. So what would a confirmed detection of these primordial B modes actually tell us? It would reveal the energy scale of inflation, telling us just how powerful that initial growth spurt truly was. It might even offer our first experimental clues to the quantum nature of gravity, bridging the largest and smallest scales of physics. These polarization imprints are the most delicate part of our photons message, a secret carried with unwavering fidelity across nearly 14 billion years. And as this ancient traveler finally approaches our cosmic neighborhood, its long journey is almost complete. This faint, uniform glow is the ultimate cosmic fossil, a snapshot of the universe at just 380,000 years old. It is the cosmic microwave background, a relic radiation that fills every direction of the sky with a temperature of just 2.7 Kelvin. Its discovery in 1965 was a masterpiece of accidental science. Arno Penzias and Robert Wilson at Bell Labs were troubleshooting a persistent, irritating hiss in a giant radio antenna, a noise they could not eliminate no matter what they tried. They had, in fact, stumbled upon the cooled remnant of the Big Bang itself, a discovery that would earn them the Nobel Prize. This ancient light is not perfectly smooth, however. It is imprinted with a tapestry of incredibly subtle patterns, temperature fluctuations of just a few parts in 100,000. Mapping these tiny wrinkles has been the life's work of space observatories like COBE, WMAP, and Planck. As Nobel laureate George Smoot famously stated, these minute variations are the blueprints for all structure in the universe. The spectrum of this radiation is a nearly perfect blackbody, a telltale signature of its origin in the hot, dense early universe. But it is the specific patterns in its temperature, the anisotropies, that hold the deepest secrets. When cosmologists analyze these patterns, they create what is known as a power spectrum, a graph that reveals a series of peaks and troughs. The angular scale of the very first acoustic peak is particularly profound. Its size tells us that the universe is geometrically flat on large scales, a pivotal finding that strongly supports the theory of cosmic inflation. Those tiny temperature variations you see on the map correspond directly to regions of slightly different density in the early plasma. The slightly warmer, denser spots had more gravity, and over billions of years, they pulled in more and more matter, eventually collapsing into the vast cosmic web of galaxies and clusters we see today. So how does this detailed analysis allow us to take a cosmic inventory? The precise ratios of the peaks in the power spectrum act as a cosmic recipe book. They allow scientists to calculate with remarkable precision that ordinary matter, the stuff of stars and planets, makes up less than 5% of the universe. Dark matter, which governs the growth of structure, accounts for about 27%. The overwhelming majority, around 68%, is the mysterious dark energy driving the accelerated expansion of the cosmos. This relic map is the fundamental backdrop for our photon's entire journey, the stage upon which all later cosmic history has played out. For billions of years, our photon has navigated the largest structures in existence, a cosmic web of staggering scale and emptiness. It flies through filaments of dark matter laced with galaxies, past immense clusters where thousands of galaxies swarm like bees, and across vast, silent voids so empty they stretch for hundreds of millions of light years. This entire architecture, this sponge-like structure of the cosmos, grew from those tiny temperature ripples we see in the cosmic microwave background. Gravity acted as the master sculptor, patiently amplifying those minute primordial flaws over eons, pulling matter into dense knots and leaving behind tremendous emptiness. As astrophysicist Dr. Karen Lee describes it, the cosmic web is like a sponge with galaxies clustered along filaments and knots, separated by enormous empty regions. This is the landscape our photon must traverse, and its journey is not a simple one. The path is a winding course through this evolving gravitational terrain. When the photon flies into a deep gravitational well, like that surrounding a massive cluster, it must climb out. As it struggles against the pull of gravity, it loses energy and its light is redshifted. Conversely, if it falls into a potential well, it gains energy and is blue-shifted. This process, repeated countless times across the entire journey, is known as the integrated Sachs-Wolfe effect. It leaves a subtle but distinct imprint on the temperature of the cosmic microwave background at the very largest angular scales. This effect becomes a powerful probe of dark energy. In a universe dominated by dark energy, the expansion accelerates, causing large-scale gravitational potentials to decay over time. A photon passing through a decaying potential well will experience a net energy loss, creating a specific, measurable correlation between the hot and cold spots on the ancient CMB sky and the distribution of galaxies we see in the universe today. Massive surveys like the Sloan Digital Sky Survey have mapped the positions of millions of galaxies, revealing the detailed topology of this web and providing the data needed to see this correlation in action. How does this photon's interaction with the cosmic architecture help us measure the growth of structure and constrain dark energy models? By carefully studying this integrated Sachs-Wolfe imprint, cosmologists can track how quickly the universe's large-scale structures have formed over time, offering a crucial test for our theories of cosmic evolution. This grand navigation through the web is the final large-scale chapter of the photon story, a journey that now brings it to the frontier of our own local universe. The long cosmic dark age did not last forever. Hundreds of millions of years after the Big Bang, a new dawn began to break, not with a single flash but as a slow, creeping sunrise across the cosmos. The first stars and galaxies ignited in the darkness, and these pioneer suns were unlike any that would follow. They were behemoths, hundreds of times more massive than our own sun, and they burned ferociously hot and bright, flooding the universe with a brutal torrent of ultraviolet radiation. This intense light began a second great transformation, known as the Epoch of Reionization. It systematically ripped electrons away from the neutral hydrogen atoms that had filled space, turning the transparent universe back into a partially ionized plasma. But this time the fog was patchy and full of holes. As researcher Dr. Michael Brown explains, reionization is a key milestone in cosmic history, driven by the first generations of stars and quasars, and it imprints a signature on the CMB polarization. Imagine bubbles of clear, ionized gas growing around these first luminous objects, slowly expanding and eventually overlapping until the entire cosmic medium was transparent once more, this time to higher energy photons. This process was not instantaneous. It unfolded over several 100 million years, a protracted struggle between light and neutral matter. We see the evidence for this in the light of the most distant quasars. Their spectra show deep, dark gaps known as Gunn-Peterson troughs, indicating that their light has been absorbed by vast reservoirs of neutral hydrogen along its path to us. Data from the Planck satellite helped pin down the timeline, suggesting reionization was largely complete when the universe was about 1 billion years old, at a redshift of around z equals 8. How does studying this reionization history help us understand the formation of the first galaxies? It reveals the powerful feedback processes at work. The same ultraviolet light that cleared the cosmic fog also heated the surrounding gas, likely suppressing the formation of the very smallest galaxies and shaping the growth of the first large-scale structures. This great relighting of the cosmos left its own subtle fingerprint on our traveling photon. The scattering of light during reionization imprinted a specific, large-angle pattern on the polarization of the cosmic microwave background, a ghostly echo of the universe's second birth. This mark is the final major entry in our photon's cosmic passport, a testament to the epic struggle between the first light and the lingering darkness. With this chapter closed, the photon's path was now clear for the final leg of its journey, through a modern universe teeming with the mature structures born from its ancient origins. Even as it nears its final destination, our photon's journey is not yet over. It now enters the diffuse outer halo of a galaxy, a vast and invisible realm dominated by dark matter. This halo is a ghostly sphere that extends hundreds of thousands of light years beyond the galaxy's bright disk of stars, containing the overwhelming majority of its total mass, yet it remains almost perfectly transparent. Here, the photon's path is subtly steered by the gravitational pull of this unseen substance, a gentle curve in the void. As dark matter expert Dr. Nina Patel explains, the distribution of dark matter in halos can be probed through weak gravitational lensing, as it bends the light from background galaxies in a characteristic way. This is how we know these halos exist at all. Although our single photon experiences only a minuscule deflection, the collective distortion of millions of background starlights paints a clear picture of the halo's shape and density. These observations reveal that dark matter halos are not uniform blobs. They follow a specific density profile, often described by the Navarro-Frenk-White model, which means they are densest at the core and become gradually more diffused toward the edges. This structure was not born this way. It formed over billions of years as dark matter collapsed under its own gravity. Sometimes, the photon's path takes it through a cluster of galaxies, where it may encounter the hot, ionized gas that is trapped within the dark matter's gravitational grip. When this happens, a small percentage of these ancient photons can collide with the high-energy electrons in this gas. This interaction, known as the Sunyaev-Zeldovich Effect, gives the photon a slight energy boost, scattering it to a higher frequency and leaving a cold spot in the cosmic microwave background at that particular location. How do these subtle interactions provide such powerful, indirect evidence for dark matter? The answer lies in the sheer mass required to explain them. The amount of gravitational lensing we observe and the presence of such incredibly hot gas point to a gravitational source far greater than the visible stars and gas alone can account for. By meticulously measuring these faint deflections and energy shifts, astronomers can effectively weigh entire galaxies and clusters, calibrating the mass estimates that confirm dark matter's dominant role. This stealthy passage through the galactic halo is a final, quiet testament to the invisible architecture of the cosmos, a structure our photon has navigated for eons. And now the final landmark emerges from the darkness, the familiar spiral arms of its ultimate target, the Milky Way. The photon now slips into the galaxy's bustling interior, a realm far from empty. It enters the interstellar medium, a sprawling ocean of gas, dust, and energetic particles that fills the vast spaces between the stars. This is not a uniform void, but a dynamic ecosystem with distinct phases, each affecting light in its own way. Dense, cold molecular clouds serve as stellar nurseries, while warm, neutral hydrogen gas forms the bulk of the medium. Hot, ionized gas from stellar winds and supernova creates vast bubbles and coronae. As interstellar medium specialist Dr. Oliver King explains, dust grains in this medium can polarize starlight by aligning with galactic magnetic fields, and they also cause extinction and reddening by scattering shorter wavelengths more efficiently. This is why distant stars appear both dimmer and redder than they truly are, their blue light scattered away by microscopic obstacles. Imagine a photon of visible starlight. It might be absorbed by a tiny dust grain and re-emitted as a faint glow in the infrared, its original journey cut short and transformed. Its path could be subtly refracted or bent as it passes through a dense cloud. Our specific photon, however, is a relic from the cosmic microwave background. Its microwave wavelength allows it to pass through most of this material largely unscathed, like a large ship sailing through a fine mist. The greater challenge is not for the photon itself, but for the astronomers trying to detect it. Foreground emission from the interstellar medium creates a fog of competing signals. Synchrotron radiation, generated by cosmic ray electrons spiraling around magnetic field lines, emits a diffuse radio glow. Thermal emission from warm dust adds a pervasive infrared and microwave haze. In regions like the galactic plane, the density of this material is so high it can completely obscure our view of the universe beyond. So how do astronomers model and remove these complex foregrounds to isolate the pristine CMB signal from cosmological origins? They use multi-frequency observations, scanning the sky across many different wavelengths. Each component of the interstellar medium has a unique spectral signature, a specific way its brightness changes with frequency. By building sophisticated models of these emissions, scientists can digitally peel them away, layer by layer, to reveal the clean, ancient light beneath. This meticulous process of foreground subtraction is a final, crucial hurdle in the photon's long journey, a necessary step to clear its path as it approaches the familiar territory of our own solar system. The solar system is a mere speck in the photon's epic journey, a final archipelago of worlds it passes in an instant. After traversing billions of light years, the gravitational pull of planets and asteroids is insignificant, their masses far too small to meaningfully bend its path over such cosmological distances. As solar system dynamicist Dr. Rachel Adams notes, for CMB photons, the solar system is essentially transparent. The main concerns are instrumental and not gravitational when it comes to detection. The Sun's gravity is the most notable local influence, potentially causing a minuscule lensing effect or a tiny redshift, but these are negligible compared to the grand distortions it has already experienced. The true challenge at this final stage is not the journey itself, but the motion of the observer. Our planet is not sitting still in the cosmos. The Earth orbits the Sun orbits the galactic center, and the entire Milky Way is hurtling through space. This complex motion relative to the rest frame of the cosmic microwave background creates a dominant signal known as the dipole anisotropy. It is as if we are sailing through a silent, gentle rain. The rain appears to fall more intensely on the front of the boat and less on the back. In the same way, the CMB appears slightly hotter, its photons slightly more energetic in the direction of our motion and cooler in the opposite direction due to the Doppler effect. This dipole is not a feature of the ancient universe. It is a fingerprint of our own local journey. Satellites like COBE have measured this signal with incredible precision, revealing that our solar system is moving at about 630 kilometers per second relative to the primordial light. How does accounting for this kinematic dipole help cosmologists isolate the intrinsic CMB anisotropies that reveal the universe's early conditions? This vital step is like a detective carefully removing a suspect's own fingerprints from a piece of evidence to reveal the true culprit's mark. By digitally subtracting this large, dominant dipole pattern from the full sky map, scientists peel away the effect of our local motion. What remains are the far subtler intrinsic temperature fluctuations, the primordial ripples that are the true blueprints of cosmic structure. This meticulous subtraction is the final act of cosmic cleaning, preparing the signal for its ultimate encounter. After its unimaginably long voyage, the photon now approaches the last barrier, the technology built to finally hear its story. This final detection is a technological ballet of extreme precision. The photon, after its 14 billion-year voyage, is intercepted by a telescope like the Atacama Cosmology Telescope or the Planck satellite. These are not simple lenses pointed at the sky, but cryogenically cooled marvels engineered to sense the faintest whispers of the cosmos. Their detectors, often arrays of bolometers, are chilled to a fraction of a degree above absolute zero. At these cryogenic temperatures, their own internal heat noise is almost eliminated, allowing them to perceive the minuscule energy of a single microwave photon. As instrumentalist Dr. Thomas Wright explains, modern CMB detectors operate at temperatures near absolute zero to minimize noise, allowing them to discern temperature variations of a few microkelvin. When our photon strikes the ultra-cold absorber in a detector, it delivers a tiny pulse of heat. This minute temperature change is then converted into an electrical signal, which is amplified millions of times and meticulously digitized, transforming the ancient light into a stream of ones and zeros for supercomputers to analyze. This entire apparatus is designed to map the sky with incredible efficiency. Detectors are arranged in vast focal plane arrays, capturing a wide field of view in a single observation. They do not look at just one frequency, but scan across many, from around 30 to over 800 gigahertz. This multi-frequency approach is the key to isolating the true cosmic signal. As we saw, the interstellar medium glows with its own microwave light from dust and synchrotron radiation, but each of these foregrounds has a unique spectral fingerprint. By observing the same patch of sky at 9 different frequencies, as the Planck mission did, scientists can build a detailed model of these local emissions and digitally subtract them, peeling away the modern galaxy to reveal the pristine universe beneath. How do advances in detector technology, such as transition edge sensors or kinetic inductance detectors, improve the resolution and sensitivity of CMB experiments? These next-generation devices can count individual photons with even greater efficiency, pushing the limits of what we can see. They reduce noise to such a degree that the subtle polarization patterns, the B modes, come into sharper focus, potentially revealing the universe's very first tremors. Yet, even the most perfect data is useless without absolute calibration. Astronomers use the CMB dipole itself, that signature of our own motion, or the predictable microwave emission from planets like Jupiter, as standard candles to ensure every measurement is anchored in reality. This entire symphony of cold, light, and data exists for one purpose: to faithfully record the story our photon has carried since the beginning of time. That raw stream of digital ones and zeros is a chaotic symphony of signal and noise. It holds the faint cosmic whisper, but it is buried beneath a cacophony of terrestrial interference, instrumental hiss, and the glow of our own galaxy. Transforming this torrent into a pristine map of the infant universe is a monumental feat of digital archaeology. The process begins with the time-ordered data, a long list of voltage readings from the detector, each one time stamped with the telescope's exact pointing direction. This data is far from a clean picture, it is a scrambled message. As data scientist Dr. Lisa Green explains, map-making in CMB experiments is an inverse problem where we reconstruct the sky signal from noisy, scanned data, often using techniques like maximum likelihood or destriping algorithms. The first step is a careful calibration, correcting for the detector's own personality, its slight gain variations and drifts in sensitivity over time. The data is then meticulously filtered to remove known contaminants, like the subtle but persistent emission from Earth's atmosphere or the rhythmic thermal noise from the satellite itself. Once cleaned, the billions of individual data points are binned into pixels on a virtual sphere, a celestial mosaic. Each pixel's temperature is not a simple average, but a statistically optimal value calculated from every time the telescope scanned across it. This is the heart of the map-making process, a complex mathematical inversion that pieces together a coherent image from millions of overlapping, noisy measurements. The result is a set of initial sky maps, but they are still a confused blend of the ancient cosmic background and local astrophysical foregrounds. The final, crucial step is component separation, a digital unraveling of these different signals. Methods like the internal linear combination or sophisticated parametric fitting in codes such as Commander and SMECA, used by the Planck collaboration, exploit a fundamental difference. The CMB has a very specific blackbody spectrum, while galactic dust emits more strongly at higher frequencies and synchrotron radiation has a different spectral slope. By comparing the maps across multiple frequencies, these algorithms can identify and isolate each component, effectively subtracting the bright veil of the Milky Way to reveal the uniform, ancient glow beneath. How do these processing techniques ensure the final maps accurately represent the primordial CMB, free from biases introduced by the instrument or environment? The entire pipeline is rigorously tested against millions of simulations, where a known CMB signal is hidden in fake data that perfectly mimics the telescope's noise and systematic errors. Only when the pipeline can perfectly recover the input signal from these simulated challenges can it be trusted with the real universe's data. This meticulous transformation from raw signal to cosmic map is the final decoding of our Photons message, a translation that prepares its ancient story for its ultimate reading. This final map of the ancient sky is more than a picture, it is a cosmic musical score waiting to be read. To understand its composition, scientists perform a powerful transformation, translating the intricate temperature patterns into a simple graph known as the angular power spectrum. This graph plots the strength of the temperature fluctuations against their size on the sky, and its shape tells the entire history of the infant cosmos. The most striking features are a series of distinct peaks, the acoustic peaks, which are the direct fingerprints of sound waves that once rippled through the primordial plasma. As theorist Dr. James Wilson states, the positions and heights of the acoustic peaks in the CMB power spectrum are like cosmic barcodes, each telling a story about the physics of the early universe. The first and tallest peak is particularly profound. Its angular scale corresponds to the size of the sound horizon at the moment of recombination, the farthest distance a sound wave could have traveled before the universe became transparent. The specific size we measure tells us that the universe is geometrically flat on large scales, a pivotal finding that confirms a key prediction of cosmic inflation. The subsequent peaks are not just echoes, they are a detailed record of the tug of war between gravity and radiation pressure in the early plasma. Gravity would pull matter inward, trying to collapse a region, while the intense radiation pressure would push it back out, creating a series of oscillations like a spring bouncing back and forth. The second peak reveals the strength of that rebound. Its height is sensitive to the density of ordinary matter, or baryons. More baryons mean more gravitational pull, which dampens the rebound and makes this second peak smaller relative to the first. The precise ratio of the odd to even peaks provides a direct measurement of the universe's baryon density, a number that has been spectacularly confirmed by independent calculations from Big Bang nucleosynthesis, which predicts how much hydrogen and helium was forged in the universe's first few minutes. But the temperature data is only part of the story. The polarization power spectra add another layer of clarity. The cross-correlation between temperature and E-mode polarization, known as the TE spectrum, provides a clear marker for when reionization occurred, as the scattering of light during that epoch imprints a specific signature. How does fitting theoretical models to this entire observed power spectrum allow cosmologists to determine the 6 parameters of the standard lambda CDM model with such high precision? The answer lies in the unique way each parameter changes the graph's shape. The density of dark matter affects how the peaks are spaced. The density of ordinary matter controls their relative heights. The expansion rate of the universe shifts their positions. By running millions of computer simulations, each with a slightly different mix of these parameters, and comparing the resulting theoretical spectrum to the one we actually observe, scientists can identify the single, perfect combination that matches our reality. This is how a single graph, derived from the ancient light of our photon, gives us a precise recipe for the entire cosmos. Decoding this blueprint is the ultimate outcome of the photon's journey, a revelation that brings us face to face with the fundamental constants of our existence. These precise values are the universe's own identification card, a set of numbers painstakingly extracted from the ancient light. The Hubble constant, the density of dark matter, the density of dark energy. These are not abstract ideas but the fundamental ingredients and settings for our cosmos, defining its composition, its expansion rate, and its ultimate fate. We know these numbers because the pattern of hot and cold spots in the cosmic microwave background acts like a cosmic lock, and the theoretical models are the only key that can open it. Scientists compare the observed power spectrum, that graph of acoustic peaks, against billions of computer-simulated universes, each with a slightly different mix of these parameters. They use sophisticated statistical methods, like Markov chain Monte Carlo sampling, to find the single combination that perfectly matches the data we see. As cosmologist Dr. Emma Davis states, the CMB is a Rosetta Stone for cosmology. It translates the primordial fluctuations into numbers that define our universe, such as the age of 13.8 billion years and the fact that ordinary matter makes up only about 5% of the total density. The results are astonishingly precise. Data from the Planck satellite constrain the Hubble constant, the current expansion rate of the universe, to about 67.4 kilometers per second per megaparsec. Yet this number sits in a growing tension with measurements from supernova in the local universe, which suggest a faster expansion rate. This discrepancy is not a failure but a tantalizing clue. It hints that our standard model of cosmology, while incredibly successful, might be incomplete, pointing toward new physics we have yet to discover. The CMB also delivers a definitive verdict on the composition of the cosmos. It tells us that dark energy, the mysterious force driving the accelerated expansion, constitutes about 68% of the universe. Dark matter makes up about 27%, leaving the familiar world of atoms, planets, and stars as a mere 5% afterthought. Even the initial conditions of the Big Bang are encoded here. Parameters like the spectral index of the primordial fluctuations tell us how the density of those early seeds varied with scale. A value of 1 would mean the fluctuations were perfectly scale invariant, but the data favor a number slightly less than 1, at about 0.965. This small but crucial deviation is a direct prediction of many inflationary theories, a subtle footprint from the universe's explosive first moment. How do these parameter determinations from the CMB cross-check with other cosmological probes? The answer lies in a powerful convergence of evidence. Baryon acoustic oscillations, the frozen remnants of those ancient sound waves seen in the distribution of galaxies, provide a standard ruler that independently confirms the expansion history. Distant supernova surveys directly chart the acceleration driven by dark energy. The fact that these entirely different methods, one looking at the very beginning and the other at the recent universe, agree on the same basic cosmic recipe is a triumph of modern science. It means we are reading the story correctly, yet for all we have decoded, the light from the cosmic dawn has also illuminated profound new mysteries, questions that now define the very frontier of cosmology. Yet this cosmic blueprint, for all its precision, holds stubborn wrinkles that refuse to be smoothed away. The most significant of these is the Hubble tension, a growing discrepancy that pits the early universe against the modern one. Measurements from the Planck satellite, which read the cosmic microwave background, give us one value for the universe's current expansion rate. But when astronomers use the SH0ES collaboration to observe distant supernova and Cepheid variable stars in the local universe, they get a consistently faster rate. This is not a small margin of error. It is a persistent and significant gap that has only widened with better data. As anomaly researcher Dr. Robert Hill explains, the Hubble tension, if real, could indicate new physics like early dark energy or neutrino interactions. One compelling idea is that a form of dark energy may have briefly surged in the universe's first few 100,000 years, subtly altering the sound horizon imprinted on the CMB and throwing off our early universe calculations. Then there are the spatial anomalies, strange features on the map that defy simple explanation. The CMB cold spot is an unusually large and deep region in the southern sky, a vast cold patch that some have speculated could be the imprint of a cosmic texture, a defect in the fabric of spacetime from the universe's earliest moments. Others suggested it was caused by a gigantic supervoid, an immense emptiness that would redshift the light passing through it, but detailed surveys have failed to find a void large enough or empty enough to account for the effect. Perhaps the most philosophically troubling anomaly is the hemispherical asymmetry. The standard model of inflation predicts a universe that is statistically the same in every direction. But the fluctuations in one hemisphere of the CMB sky are slightly larger than in the other, as if the universe has a preferred axis. Other curiosities include the mysterious alignment of the lowest multipoles, the largest possible waves on the cosmic map, which seem to point in a similar direction, and a puzzling lack of correlation on the very largest angular scales. How do ongoing and future CMB experiments aim to resolve these tensions? Projects like the Simons Observatory and the upcoming CMB S4 are being built with unprecedented sensitivity. They will scan the skies with tens of thousands of new detectors, hunting for the faint polarization signals that could reveal early dark energy or the unique swirls of gravitational waves from inflation. By providing exquisitely detailed maps of both temperature and polarization, these observatories will stress-test our models like never before, either confirming these anomalies as real physics or exposing them as subtle statistical flukes. These unresolved puzzles are a vital reminder that our photon story is not yet fully told. its ancient message still contains layers we have not learned to read, hinting at chapters of cosmic history waiting to be discovered in the darkness. The frontier of cosmology is being redrawn by a new generation of observatories, instruments of such breathtaking sensitivity they will listen to the universe's first whisper with unparalleled clarity. Projects like the Simons Observatory, the colossal CMB S4, and the space-based LightBird mission are preparing to deploy not dozens, but tens of thousands of next-generation detectors. Their primary target is the most elusive prize in cosmology, the primordial B-mode polarization, the signature of gravitational waves from the universe's inflationary birth. To achieve this, they must operate in environments of extreme quiet. Ground-based telescopes will peer skyward from the bone-dry, thin air of the Chilean Atacama Desert, while LightBird will observe from the perfect silence of space, eliminating the last vestiges of atmospheric interference and systematic noise. As project scientist Dr. Maria Lopez explains, CMB S4 aims to measure the tensor to scalar ratio to a precision of sigma of r less than 0.001, which could confirm or rule out many inflationary models. This is not just an incremental improvement, it is a leap into a new regime of precision, capable of detecting a signal 100 times fainter than our current limits. The scientific yield extends far beyond this single goal. By mapping the small-scale polarization and temperature variations with microscopic detail, these observatories will place stringent new constraints on the total mass of neutrinos, those ghostly particles that stream freely through the cosmos. They will refine our understanding of dark energy's nature and pin down the exact timeline of the Epoch of Reionization. Each mission has a specialized focus. LightBird, a JAXA-led space mission, is uniquely designed to scan the entire sky at large angular scales, hunting for the inflationary B-mode signal across the vastest cosmic horizons. This requires advanced technologies like multichroic detectors that can observe multiple frequencies simultaneously and large aperture telescopes that gather immense amounts of light, enabling both higher resolution and broader frequency coverage to better separate foregrounds. How will these future data sets help address current cosmological tensions and potentially discover new physics beyond the standard model? The answer lies in their raw statistical power. The immense volume of pristine data will subject our best models to stresses they have never faced, potentially revealing the subtle cracks that point toward a deeper theory. The quest to fully decode our photons message is accelerating, pushing the boundaries of technology and imagination. And as we learn to read this ancient light with new eyes, we find it speaks a language shared by other, more dramatic cosmic messengers. This ancient light does not travel alone. Its story intertwines with other, more elusive cosmic messengers, creating a richer, multi-dimensional picture of the universe. By correlating the cosmic microwave background with signals like gravitational waves, neutrinos, and high-energy gamma rays, we practice multi-messenger astronomy, a powerful approach that cross-validates our models and reveals processes no single signal can uncover. As multi-messenger advocate Dr. Kevin Zhao explains, the correlation between CMB lensing maps and gravitational wave events can test the propagation of gravity and the distribution of dark matter. Imagine a ripple in spacetime detected by LIGO and Virgo from the collision of two black holes. That gravitational wave traveled across the universe, and its path was subtly shaped by the same dark matter web that gently lensed our CMB photon. Comparing these two journeys provides an independent test of how gravity behaves over cosmic distances. The integrated Sachs-Wolfe effect that subtle energy loss from photons climbing in and out of gravitational wells finds another partner in vast galaxy surveys. By cross-referencing the cold and hot spots on the ancient CMB sky with a three-dimensional map of galaxies from projects like the Sloan Digital Sky Survey, cosmologists can place tight constraints on the nature of dark energy and how it has influenced the growth of structure. Even the violent motion of galaxy clusters leaves a mark. The kinetic Sunyaev-Zeldovich effect, a slight shift in the CMB's temperature caused by hot gas moving within clusters, traces their bulk momentum, offering a way to weigh these colossal structures dynamically. The ultimate synergy may lie in the hunt for inflation's first tremors. A future detection of primordial B-mode polarization in the CMB would be a monumental discovery. That signal could then be complemented by direct observations from space-based gravitational wave observatories like LISA, which might detect a stochastic background of low-frequency waves from the same inflationary epoch. How do these synergistic observations enhance our understanding of phenomena like inflation, reionization, and large-scale structure formation? They force our theories to be consistent across completely independent lines of evidence. The timeline of reionization pieced together from the CMB's polarization must agree with the history written in the light of the earliest quasars and galaxies observed by the James Webb Space Telescope. The universe is telling the same story in multiple languages, and we are finally learning to listen to them all at once. This integrated view transforms our photon from a solitary relic into one voice in a grand cosmic chorus, its journey part of a vast, interconnected tapestry of information. This ancient light does more than illuminate the cosmos, it illuminates our own place within it. Detecting a photon from the cosmic dawn is an act of touching the origin of everything, a direct connection to the universe's fiery infancy that places our fleeting moment in a vast cosmic narrative. We are not just passive observers looking out at a distant sky, we are active participants receiving a message sent long before our world, or even our sun, ever existed. This realization is profoundly humbling. As philosopher of science Dr. Anna Bell remarks, the cosmic microwave background is a testament to the power of human curiosity. It allows us to witness the aftermath of creation and ponder our minute yet significant role in the cosmos. The very uniformity of this light, the same faint glow in every direction, tells a story of common origin. Every galaxy, every star, every living thing, and every one of us is crafted from the same primordial ingredients forged in that initial furnace and detailed in this ancient blueprint. We are, in the most literal sense, the universe becoming aware of itself. This cosmic context inevitably reshapes our perspective. Contemplating a timeline of 13.8 billion years, an observable universe bounded by this faint horizon of first light, challenges our deepest intuitions about eternity and our own significance. It raises profound questions about the nature of time itself and whether our universe is but one bubble in a potentially infinite multiverse, a concept hinted at by the strange initial conditions that inflation sought to explain. How does this grand scale influence our ethical and existential considerations about humanity's future and responsibilities? Understanding our shared cosmic heritage and the fragility of our pale blue dot can foster a sense of global stewardship, a recognition that our future, whatever it may be, is a collective chapter in this ongoing story. The photon's journey thus becomes more than a scientific marvel. It is a philosophical guidepost. Its detection proves that the same physical laws govern the birth of galaxies and the workings of our detectors, a universality that makes comprehension possible. We are small, but we are not blind. We are ephemeral, but we can perceive eternity. This knowledge, born from ancient light, now powers the technology that defines our modern world. This ancient light does more than chart the cosmos. It ignites the spark of discovery in a new generation. The epic journey of a single photon, from the first scattering to its final click in a detector, is a powerful story that can transform how we teach science. By framing cosmology as a grand narrative, we make abstract ideas like the Big Bang and cosmic inflation accessible and deeply engaging for students and the public alike. Educator Dr. Susan Clark affirms that telling the story of a photon from the early universe to a detector makes cosmology tangible and inspires awe, which is a powerful motivator for learning. This story comes alive in Planetarium, shows that visually map the photon's voyage across billions of years, and in interactive websites where users can peel away galactic foregrounds to reveal the pristine cosmic microwave background. Imagine a classroom activity where students don't just hear about the universe's composition, they derive it themselves. Projects like the CMB Legacy Virtual Lab provide exactly this, allowing users to process mock data from a simulated sky and calculate fundamental cosmological parameters like the density of dark matter with their own hands. This hands-on experience turns abstract numbers into a personal discovery. Public lectures and documentaries that feature the diverse, international teams behind missions like Planck or the Simons Observatory do more than share facts, they humanize the scientific process. They show that science is a collaborative, often messy, and profoundly human endeavor, breaking down the stereotype of the solitary genius and highlighting its global cultural significance. How can such initiatives address educational disparities and encourage underrepresented groups to pursue careers in astrophysics and related fields? By making these resources freely available and designing them to be culturally responsive, we can reach students in underserved communities, showing them that the universe's story is their story too, and that they have a place in uncovering its next chapters. This act of sharing knowledge ensures the photon's long journey continues to enlighten minds long after its detection, weaving its ancient legacy directly into our future. The tools developed to capture this faint light have also sparked innovations that reach far beyond the cosmos, spinning off into technologies that shape our daily lives. The relentless pursuit of this ancient light has quietly revolutionized technology far beyond the telescope. To capture a whisper from the cosmic dawn, scientists had to invent entirely new ways of seeing, spawning innovations that now touch our lives in hospitals, airports, and communication networks. The extreme demands of cosmic microwave background experiments have driven breakthroughs in cryogenics, pushing the limits of how we achieve and maintain temperatures within a fraction of absolute zero. This mastery over ultra-cold environments is not just for astronomy. It is crucial for the development of powerful magnetic resonance imaging machines and the quantum computers of tomorrow. As technology transfer expert Dr. Paul Evans notes, the development of superconducting detectors for CMB studies has paved the way for new medical imaging techniques and quantum computing components. Consider the transition edge sensor, an exquisitely sensitive thermometer at the heart of modern bolometers. This same technology is now being adapted for highly precise X-ray spectroscopy, allowing materials scientists to analyze the atomic structure of new compounds and engineers to create more effective security scanners that can identify concealed threats. The challenge of processing a flood of data from space has forced the creation of sophisticated algorithms for cleaning noise and stitching together signals. These very same data compression and analysis methods, born from the need to make a cosmic map, are now applied to machine learning and big data challenges, from improving internet search engines to modeling complex financial markets. Even the precision manufacturing required to build a satellite like Planck, where every component must perform flawlessly in the vacuum of space, has raised the bar for engineering and metrology, improving the quality control standards for everything from consumer electronics to automotive parts. How do these cross-disciplinary applications demonstrate the value of fundamental research and its potential to drive economic and technological progress? They prove that by asking the most profound questions about the universe, we are often forced to invent the tools for our own future, spinning off solutions to practical problems we had not yet even conceived. This legacy of innovation is a powerful testament to the photon's journey, proving its impact extends from the grandest cosmic scales to the most tangible aspects of our daily world. Translating the intricate story of this ancient photon into something we can all grasp is a creative act of its own. Science communicators work as bridges, transforming complex data into engaging narratives, vivid animations, and relatable analogies that preserve the truth of the discovery while making it accessible. This work is vital, fostering the public understanding and support that allows fundamental research to continue. As communicator Dr. Hannah Lee explains, using metaphors like comparing the cosmic microwave background to the surface of a boiling pot that suddenly froze, can help people grasp the concept of primordial fluctuations. That simple image captures the idea of a dynamic, seething universe instantly locked into a pattern, its tiny bubbles and ripples becoming the seeds for all future structure. Visualizations play a crucial role in this translation, an animation that traces the photon's path from its moment of decoupling through the expanding cosmic web and into the heart of a cryogenic detector, turns an abstract 14 billion-year journey into a tangible, visual story we can follow. Interactive exhibits in science museums take this a step further, offering immersive experiences. Imagine a visitor donning a virtual reality headset to find themselves floating in the early universe, able to reach out and touch the hot and cold spots of the cosmic microwave background as they form, feeling the scale of those primordial seeds. Yet, this work is filled with subtle challenges. The biggest pitfall is oversimplification, stripping away the nuance and uncertainty that are inherent to the scientific process. How can communicators balance excitement about a major discovery with an honest discussion about its limitations or the ongoing debates within the scientific community? The answer lies in building trust by presenting science not as a list of unchangeable facts, but as a rigorous, self-correcting process of inquiry. It means acknowledging when a result is preliminary, explaining the statistical confidence behind a claim, and highlighting the unanswered questions that drive researchers forward. This clear, honest communication ensures that the profound wonder of the photon's journey is shared by everyone, not just a select few. And as this knowledge spreads, it naturally leads us to a deeper, more personal reflection on what this cosmic connection means for our own place in the universe. While the quest for ancient light seems like a purely noble pursuit, it arrives with a profound ethical weight. The same technological leaps that allow us to decode the cosmic dawn can also be repurposed in ways their creators never intended. The ultra-sensitive detectors and advanced data processing algorithms developed for CMB telescopes possess an inherent dual-use potential. As ethicist Dr. Omar Khan observes, the power to model the universe's beginnings comes with a responsibility to use that knowledge for the benefit of humanity and to respect diverse perspectives on creation. The cryogenic sensors designed to catch a single photon from the edge of time could be adapted for high-resolution surveillance systems. The sophisticated software that peels away galactic foregrounds could be used to analyze and track personal data on a massive scale. This is not a call to halt discovery, but a necessity for proactive guidelines that steer innovation toward healing, communication, and understanding, rather than control and conflict. Beyond the hardware, the cosmological story itself can challenge deeply held beliefs. When science presents a narrative of a universe emerging from a hot, dense state nearly 14 billion years ago, it may stand in stark contrast to traditional creation accounts. This does not make one right and the other wrong, but it highlights a critical need for dialogue. The scientific community bears a responsibility to share its findings with cultural sensitivity, presenting the Big Bang not as a cold, atheistic fact, but as a modern creation myth backed by evidence, one that speaks to a shared human wonder about our origins. This requires scientists to be not just researchers, but also communicators and listeners, engaging with religious leaders and community elders to find a common language of awe. How can we share the epic of the cosmos in a way that unites rather than divides, that adds a chapter to humanity's collective story instead of erasing the ones that came before? This introspection extends to the very resources we dedicate to this exploration. Building a billion-dollar space telescope or a vast ground-based observatory is a monumental investment. In a world grappling with poverty, disease, and climate change, it is fair to question the priority of studying the first light of the universe. The justification lies not in dismissing earthly problems, but in the long-term returns. The history of science shows that fundamental research, pursued for its own sake, consistently yields unforeseen practical benefits. The very internet that connects global efforts to fight pandemics was born from the need for physicists to share data. The pursuit of cosmic knowledge inspires new generations of engineers, doctors, and problem solvers, fostering a global perspective that recognizes our shared existence on a fragile planet. The challenge is to ensure this cosmic perspective translates into tangible earthly benefits, aligning the quest for origins with the urgent need to improve the human condition. These ethical layers are an inseparable part of the Photons' legacy, reminding us that every step into the cosmos must be taken with thoughtful consideration for our world and all its people. That faint whisper from the beginning of time has echoed far beyond the walls of our observatories, resonating deeply within the human imagination. The cosmic microwave background has become a powerful cultural symbol, its mottled map of hot and cold spots appearing in art installations, film sequences, and even textile designs, transforming raw scientific data into a universal language of origin. As cultural historian Dr. Isabella Rossi explains, artists have used CMB maps as visual motifs in installations and films, transforming scientific data into aesthetic experiences that evoke wonder and contemplation. This is more than just decoration. It is a profound dialogue between two ways of understanding our place in the cosmos. The specific pattern of the universe's first light, a snapshot of quantum fluctuations stretched across the sky, is now a visual shorthand for the deepest mysteries of existence. You can hear its influence in experimental music compositions where the temperature fluctuations of the CMB are translated into a symphony of sound, each note representing a tiny variation in the density of the infant universe. You can see its imprint in high fashion, where designers have woven the map's texture into fabrics, wearing the blueprint of creation as a statement on the connection between humanity and the cosmos. In literature, the narrative of the Big Bang and the subsequent journey of light provides a grand framework for stories exploring identity, memory, and our fleeting moment within an immense timeline. Authors use the cosmology not as a dry fact, but as a backdrop for human drama, asking what our lives mean in a universe that began in fire and will end in cold. Television documentaries and planetarium shows have brought this story to millions, making the abstract concept of the universe's first light a tangible and emotionally resonant part of our collective consciousness. How can collaborations between scientists and artists deepen the public's emotional and intellectual connection to cosmological discoveries? When a sculptor and an astrophysicist work together to create a physical, walk-through model of the CMB, they build a bridge. The scientist provides the precise data, the intricate story of the photon's journey, while the artist gives that story a form we can touch and feel, engaging our senses in a way a graph never could. This partnership makes the cosmos feel less distant and more like a home we are all striving to understand. It translates the mathematics of the primordial plasma into a shared experience of awe, ensuring the photon's epic journey transcends the realm of academic papers to become a living part of our culture. This widespread resonance invites everyone to participate in the story, and that invitation is now being answered by a growing movement of citizen scientists. Anyone can now join the hunt for cosmic clues from the comfort of their own home. Online platforms have thrown open the doors to cosmology, inviting the public to sift through the universe's data in citizen science projects. On websites like Einstein at Home, volunteers contribute their personal computer's idle processing power, creating a distributed supercomputer that churns through vast datasets, searching for the subtle signatures of gravitational waves or anomalous signals in the cosmic microwave background. Other projects ask participants to visually classify curious features in sky maps, tasks where the human eye for pattern still outpaces the most advanced algorithms. This movement does more than just accelerate research. It fundamentally democratizes discovery. Citizen Science Coordinator Dr. David Miller observes that involving the public in CMB research not only accelerates data analysis, but also builds a community of informed advocates for science funding. When a retiree in Lisbon or a student in Tokyo helps identify a rare gravitational lens, the resulting scientific paper carries their name. They gain a genuine sense of ownership and connection to the cosmic story, transforming them from passive observers into active contributors. Interactive archives like the Planck Legacy Archive put the same powerful sky maps used by professional cosmologists into the hands of the curious, allowing anyone to explore the subtle temperature fluctuations and perform their own simple analyses. Educational games take this a step further, turning complex concepts like gravitational lensing into engaging puzzles, effectively crowdsourcing human intuition to solve problems that computers find difficult. These initiatives are powerful educational tools, silently building scientific literacy by immersing people in the actual process of inquiry. The challenges, of course, are significant. How can these projects maintain the rigorous data quality required for publication while being accessible to newcomers? The solution lies in thoughtful design, incorporating training modules, clear guidelines, and robust feedback systems that guide volunteers and validate their contributions. How can citizen science projects be designed to maximize engagement and scientific output while maintaining rigor and inclusivity? The most successful platforms weave learning directly into the task, creating a supportive environment where every click contributes to a larger, shared goal. This collaborative model proves that the photon's epic journey does not end in a detector. It continues into our collective imagination, uniting people around the world in the grand endeavor of understanding our universe. The immense cost of capturing ancient light reveals a universe of earthly challenges. Projects like the Planck satellite required an investment of over €600 million, a sum that funds not just hardware but a global collaboration of scientists, engineers, and technicians for more than a decade. This financial gravity is anchored by major agencies like NASA, the European Space Agency, and the National Science Foundation, who must constantly justify why peering into the cosmic dawn is a worthy use of public funds. Economist Dr. Patricia Wood reminds us that while the immediate economic return of cosmology is not always clear, the long-term benefits through spin-off technologies and enhanced human capital are substantial. The pursuit of a single photon from the edge of time does not happen in a financial vacuum. Every funding decision is a deliberate choice, a weighing of cosmic curiosity against pressing terrestrial needs like medicine and infrastructure. The justification rests on a foundation of profound scientific merit, the chance to answer fundamental questions about our existence, but also on the powerful, tangible spin-offs this research generates. The same cryogenic sensors developed to hear the faint microwave whisper of the Big Bang have found new life in improving the resolution of medical MRI machines, leading to earlier disease detection. Advanced signal processing algorithms created to filter the cosmos from background noise now enhance global telecommunications networks. These innovations create new markets and skilled employment opportunities, building a high-tech workforce that benefits the entire economy. How can the cosmology community effectively communicate the value of such investments to policymakers and the public to secure ongoing support? The answer lies in telling the complete story, one that connects the quest for ultimate origins directly to the technologies that improve daily life and drive economic progress. This requires transparency about the costs and a clear vision of the long-term rewards, framing fundamental research not as a luxury, but as a crucial investment in our collective future. The epic journey of our photon is thus underwritten by a complex web of global cooperation and economic rationale, a testament to the value we place on understanding our place in the cosmos. The story of this ancient light was written decades before we ever learned to see it. In the 1940s, physicists George Gamow, Ralph Alpher, and Robert Herman made a stunning theoretical leap. They reasoned that if the universe began in a hot, dense state, it must have been filled with a brilliant, searing radiation. As this primordial fireball expanded and cooled, they predicted this light would still be all around us, stretched into a faint, cold afterglow permeating all of space. For nearly 20 years, this prediction was a beautiful but unproven idea, largely ignored and competing with the popular steady-state theory, which proposed a universe with no beginning and no end. The discovery, when it came, was a masterpiece of accidental science. In 1965, Arno Penzias and Robert Wilson at Bell Labs were troubleshooting a persistent, irritating hiss in a giant, sensitive horn antenna. They had scrubbed away pigeon droppings and checked every connection, but the unwanted noise remained uniform in every direction. They had, without initially realizing it, stumbled upon the cooled remnant of the Big Bang itself. As historian of science Dr. Linda Grant describes, the detection of the CMB was a turning point in cosmology, shifting the field from speculation to a data-driven discipline and cementing the Big Bang theory. This was not a solitary eureka moment, but the culmination of a collaborative effort that included the engineers who built that remarkable antenna. The finding resolved a major scientific debate, as the steady-state theory could not easily explain this pervasive, uniform background. But confirmation required more than just its detection. It demanded precise measurement. The Cosmic Background Explorer satellite, or COBE, delivered that proof in the 1990s, revealing with stunning clarity that the spectrum of this ancient light was a near-perfect blackbody, exactly as predicted for a relic of a hot Big Bang. The COBE team's Nobel Prize in 2006 recognized the monumental importance of turning a theoretical ghost into a measurable cosmic reality. How does this history illustrate the roles of theory, serendipity, and technology in scientific progress? It shows a beautiful dance where a bold prediction guided the search, a fortunate accident provided the first clue, and technological ingenuity ultimately confirmed the theory, transforming our entire understanding of the cosmos. This historical journey from prediction to detection reveals that the photon's epic story is intertwined with our own quest for knowledge. To truly understand its origin, we must now peer even deeper into the quantum realm where this entire cosmic saga first began to flicker. Our photon carries a secret identity rooted in the quantum realm. It exists as both a particle and a wave, a fundamental duality that defines its very nature. This is not an abstract concept, but a concrete reality underpinning its entire epic journey. As a gauge boson for the electromagnetic force, the photon is the fundamental carrier of light, and its interactions are exquisitely described by the theory of quantum electrodynamics. Yet to understand its ultimate origin, we must venture to an even more profound frontier, where gravity itself must be understood through a quantum lens. The tiny temperature variations your photon helped map onto the cosmic microwave background did not emerge from nothing. They were born from the quantum vacuum, a seething foam of energy at the universe's very beginning. During the inflationary epoch, a period of hyper-fast expansion, microscopic quantum fluctuations were stretched to astronomical sizes. What was once a tiny ripple on the quantum scale became a vast hill or valley in the density of the cosmos. As quantum cosmologist Dr. Samuel Torres explains, the CMB anisotropies are essentially amplified quantum fluctuations from the inflationary epoch, making the large-scale structure of the universe a quantum artifact. This means the entire cosmic web of galaxies, including our own Milky Way, traces its lineage back to these random subatomic tremors. The photon's own quantum character is written into its polarization. The search for the elusive B-mode pattern is a hunt for the imprint of primordial gravitational waves, which themselves are theorized to be amplified quantum fluctuations in the fabric of spacetime. This connection is staggering. It means that by studying the polarization of this ancient light, we are indirectly probing the quantum nature of gravity, a unification of physics that has eluded us for a century. How does the quantum origin of CMB fluctuations provide a unique window into the unification of general relativity and quantum mechanics? The patterns we see are a fossilized record of physics at energy scales 1 trillion times higher than any particle collider can ever reach. They are our only direct evidence of the conditions where these two great theories must merge. This quantum backdrop is the deepest layer of the photon story, revealing that the cosmos we see is, at its heart, a quantum artifact grown to cosmic proportions. To trace the full implications of this quantum beginning, we must reconstruct its entire history, not with telescopes, but with the most powerful supercomputers on Earth. Supercomputers now trace the entire arc of our photon's epic journey, not through observation but through pure calculation. These are not simple animations, they are full-scale universes born from code, evolving from the first quantum flicker of inflation all the way to the present cosmic web. Inside these virtual realms, billions of simulated photons travel along paths bent by simulated galaxies, their light stretched and scattered just as it is in our real cosmos. Projects like Illustris TNG and Bolshoi incorporate the complex physics of gravity, the swirling dynamics of galactic gas, and the subtle transfer of radiation to build a digital cosmos from the ground up. Computational astrophysicist Dr. Ryan Kim explains that simulations allow us to test cosmological models by generating mock CMB maps and observing how photons are lensed or scattered in a virtual universe. This process is a crucial dialogue between theory and reality. Scientists can input a set of assumptions, like the amount of dark matter or the strength of dark energy, and then watch what kind of cosmic microwave background their virtual universe produces. They use sophisticated ray tracing techniques, sending out millions of virtual light rays through the intricate scaffolding of simulated dark matter halos. This allows them to predict the precise weak lensing signals, the subtle shearing of light that should appear in the data. When they compare these simulated signals to the actual patterns we observe in the sky, they have a powerful test. If the mock data and the real data match, it strengthens our confidence in the underlying model. If they do not, it is a clear sign that our understanding is incomplete. These virtual laboratories are especially vital for planning the next generation of observatories. How do these computational approaches enhance our ability to interpret the CMB and plan future observations? By running countless simulations, scientists can identify subtle systematic effects that might fool our analysis, and they can explore wild, speculative scenarios that are impossible to test any other way. They can create a universe with modified laws of gravity, or one populated by additional, exotic types of neutrinos, and see what unique imprint that would leave on the ancient light. This digital experimentation reveals which future measurements will be most decisive in answering our deepest questions. The Photon's 14 billion-year voyage is thus replayed in a supercomputer in a matter of hours, a virtual homecoming that prepares us for the truths carried by the real thing. Its 14 billion-year voyage ends in a single, quiet click. From the fiery moment it broke free from the primordial plasma, to its long journey stretched and bent by the evolving cosmic web, this particle of ancient light has delivered a message across time. Its story is the universe's story, a narrative written in temperature fluctuations and polarization that we have learned to read. We now know the cosmos is geometrically flat, its expansion accelerating under the influence of a mysterious dark energy, and its grandest structures grown from microscopic quantum seeds. These are not just facts, they are fundamental truths that reshape our perception of reality itself, revealing a cosmos both vast and intimately connected to the quantum realm. This profound understanding is a testament to a monumental human endeavor. It was built by the curiosity of theorists, the ingenuity of engineers, the persistence of observers, and the global collaboration that spans cultures and disciplines. We did not just look up at the sky, we built tools to listen to its faintest whispers, and in doing so, decoded our own origin story. Yet for all we have learned, the journey is far from over. The nature of dark energy and dark matter remains elusive. The Hubble tension hints at new physics, and the quantum origin of spacetime is still a profound mystery. These unresolved questions are not endpoints but invitations. They call on the next generation of thinkers and dreamers to continue the quest. You are part of this story. Your curiosity, your support for scientific education, and your participation in citizen science projects ensure that the legacy of this ancient light will continue to illuminate our path forward. The universe has shared its first chapter with